So let's go ahead and throw everything together here, as well as talk about one other concept that we have to look at, and that is the concept of thermogenesis and ATP efficiency. So let's start off with our ATP counts per mole of glucose that comes in. And so we start with glycolysis, then we get our Krebs cycle totals, and then we get our electron transport chain or electron transport system totals, which gives us our grand totals. Now notice the grand totals don't always add up to what is given in the textbook, and that's where we have to take into account what ATP is being expended along the pathway and how the yields of ATP are being determined either due to stoichiometric balancing or due to energetic balancing. One of the things that's going to impact the total amount of ATP that's being produced per mole of substance coming into the mitochondria is the ability to link the electron transport chain, electron transport system, to the ATP synthase. There is a protein within the mitochondrial inner membrane known as an uncoupling protein, the UCP. And what the UCP is doing is that it is separating the movement of the hydrogen from the ATP synthase. It's uncoupling the electron transport system from the ATP synthase. It does this so as to stabilize the Km, or the kinematic motion of the synthase molecule. But the other thing it's doing is it's increasing the heat production. It is the process of mitochondrial thermogenesis. The uncoupling protein can allow for excessive heat production. The amount of uncoupling proteins that are available to the mitochondria are hormonally regulated. Now, there's always some amount of uncoupling protein available. However, the amount of uncoupling protein will vary based off of hormonal signaling. The other thing that the uncoupling protein does is that it reduces the efficiency of the electron transport chain. It decreases the amount of ATP being regenerated per mole of substance being consumed within the pathways. The hormones that are going to lead to upregulation of the uncoupling protein include thyroid hormones, leptin, epinephrine, which all lead to increased thermogenesis and a reduction of the efficiency of the electron transport chain. This means that we have to utilize additional fuel just to meet stable ATP demand. Within this thermogenic pathway, we have to remember is that there's a few ways that we'll look at temperature, and we'll get a little bit more into this when we talk about thermoregulation in the hypothalamus. When we look at temperature, it's a reference to where we are measuring, in which we are attempting to ensure that the core body temperature is maintained at 37 C. And we have a very narrow window of operational efficiency. If we start to elevate core body temperature by roughly 2 C, we start to experience heat exhaustion. If we go 3 C above, if we start getting to 41 C, we start experiencing heat stroke issues. The regulation of the pathway is based off of the hypothalamus, and the hypothalamus setting was referred to as a thermostat point that is going to induce an autonomic nervous system feedback loop that increases vascular flow to the dermal arterioles to increase radiative and evaporative cooling of the body. If core body temperature is elevated, It increases uncoupling protein and mitochondrial biogenesis when core body temperature is lowered. So outside of the utilization of glucose, we've talked about other fuel sources that can be used for the ATP pathways. These include pyruvate, lipids via beta oxidation, ketone bodies, proteins and amino acids, either through glucogenic or ketogenic amino acids, or amino acids forming the intermediates within the Krebs cycle. If we throw all of this together, what does the energetic pathways look like, and how are they ultimately regulated? Well, the first pathway is going to be completely enzymatically controlled, and that is the phosphagen pathway, the ATP-CP pathway. By itself, we get at most 8 to 10 seconds before we have full exhaustion of the pathway. The next pathway that comes into play is the glycolysis pathway. We get somewhere between 20 and 180 seconds with the glycolysis pathway. The glycolysis pathway is metabolite and enzymatically regulated. Diet and dietary restrictions can drastically affect glycolysis. The ability to flexibly use fuel sources can drastically affect glycolysis. The preference of fuel sources within activity can drastically affect glycolysis. Moving from glycolysis, we get to the Krebs cycle. In the Krebs cycle, we have about 3 to 5 minutes before we start to exhaust the Krebs cycle due to lack of return of NADH and FADH to the pathway to allow for it to be reduced. Buildup of metabolites within the Krebs cycle will also lead to exhaustion of the Krebs cycle. This 3 to 5 minutes is that same 3 to 5 minutes that we talk about when we look at aerobic tissues and how long can they survive without constant perfusion, without starting to suffer from infarctic issues. Linked with the Krebs cycle, we get the electron transport chain. The electron transport chain, as long as oxygen is available to it, there is no time limit to exhaustion. This will continue to undergo pathway if ATP demands are being met and we have NADH and FADH2s available. Instead of producing additional ATP, we will start to produce additional heat. And so let's throw this all together in terms of grand totals, and let's look at efficiencies here. So all efficiency is going to be based off of how efficient is the fuel source relative to glucose. All lipids are more efficient than glycolysis. We have somewhere between 1.25 and 3.4 times ATP return from the lipids relative to the mole of glucose that is coming in, which means that lipids are the greatest efficient fuel source that we have. Now, if we compare that with what we get from the deamination introduction of the carbohydrate backbones from amino acids, the return that we get is going to be dependent upon where within the cycle that amino acid derivative is coming in. But at most efficient, it's only about 75% efficient relative to glucose coming in, which means that if we have a continuum of efficiencies, lipids are more efficient than glucose, and glucose is more efficient than amino acids. We can throw in other fuel sources within there. Ketones and ketone bodies will be about as efficient as amino acids. Fructose will be slightly more efficient than glucose.